Isaiah, I don't remember giving you anything, so let's see. You've got it too. Raymond? No, I can't. Maybe I already gave you it. I don't have it. That's strange. Raymond, do you have permission? I can't tell.
I don't think I do, but I'm okay.
You're all right either way.
Yeah.
I'm not sure I can give it to you. If I can, I will. Yeah, it says I can. I think I just gave it to you.
Yeah, I see it.
Anyone else? Okay. Well, I guess updates are called for. I haven't gotten anything done on the exams, so that continues, I'm afraid. The other thing that I was doing at the end of last hour, I think it was in office hours. Was I talking about a computer, an algorithm to figure out the stationary distribution? I think I was doing that, but I think I ran out of time. That's what it was. And that was sort of sad. Anyway, I looked at it again, and it's more complicated than I thought it was going to be. I'm going to spend a few minutes on it, but I'm afraid that if I made a mistake, I could be spending too much time on this. But let me show you what I got anyway. So that much I'll do. Before turning to that, is there anyone who's going to come on board? Let me see. Cassidy, I don't remember giving you permission, but I don't see you're asking for it. So is there anyone else here to look at? Let's see who else is on. Hugo, I got two windows for you, I guess. I'm not sure why.
Yeah.
But I guess it's right. Okay, anyone else need it before I go back to just general OneNote? Okay, well, let me show you this algorithm. So this is a little departure from what we normally do. Normally, I either cover the material in the book or I just go off and explain things in my own words, my own way. And I guess this is the second category, but it's not the way that not the topic that I'm usually discussing, that's for sure. So let me see if I can get OneNote up and we can talk about this a little more. OneNote is here. Okay, I can see it. I hope you can see it now. This is something else entirely. So this is a different topic. But let me just get down to the bottom and see if I can give a. I'm not even going to look for what we did last time because I think it was done in a pretty hurried fashion anyway. I'm just going to start anew. If I can. Oh, that's interesting. Not letting me do what I want. Try again. Try this in a different way. Okay, that seems to have worked. Okay, so the question is, how do we find a stationary distribution when it exists? So that's the question. How do we find a stationary distribution pi when it exists. Just an S up there. That already is implying that they're not always stationary distributions. I'm not even sure I've answered that question, but let's start simple here. What does it mean to be a stationary distribution? Well, to be stationary for a distribution to be a stationary distribution, two things have to be true. We need that pi is equal to pi p. P is the one-step transition probability matrix. And we also need, well, if pi has, suppose pi is made up of pi 0, first entry, pi 1, second entry, all the way to the last entry. And suppose the last entry is pi n minus 1. So suppose it's a finite vector. And by making this pi n minus 1, since we started 0, there would be n different states. We need, so we require that pi 0 plus pi 1 plus all the way to the last one, pi n minus 1, total 1. Okay. So this is the main defining equation to be stationary. We've already talked about that. And to be a stationary distribution, for pi to be a stationary distribution, that's fine. I suppose we need this equation, and we need, to be a distribution, all the probabilities have to add up to 1. So we already understand that what's in here are probabilities, which are between 0 and 1, and their sum has to be 1. Now, there's a theorem, which I quoted the other day. If you have an irreducible Markov chain, then there exists a unique stationary distribution. Okay, so that addresses a little bit when it exists. So for now, we're just going to assume the Markov chain is irreducible. And this implies that there's a unique stationary distribution. Now, in order to find it, you can go back to this definition and write out a system of linear equations and solve that system. And as I've already warned you more than once, if you just use the equations here, you won't be successful. You also have to make use of this equation as well in solving for what pi would be equal to. And we did an example of that type last time we were together. And that part of what I did wasn't so hurried. That was, let me just refer to it again. That was example 1 on page 49. So we followed it. So last time we did example 1 on page 49. That's a 3x3 case. The matrix was 3x3, and it took a little time, but I pretty much followed that example verbatim, pretty much word for word. Okay. And then I said, this is only going to get harder and more tedious, I suppose. if the dimension is larger. So there's an algorithm that we can use to do this. And that's when I sort of ran out of time and it wasn't working either. So the combination that's where we left off. Any questions of where we are before we go further? So, I have something to put forward here. I'll tell you what I think the algorithm is. And I'd like to test it before we spend any time proving it, or I have to explain it a little bit in order to even test it. So here's the explanation. So let's assume. So here's a partial explanation. Even hesitate to call it that. A very thin explanation. So you might say, what do you mean by a thin explanation? I mean an explanation that really doesn't tell you at all where it came from. It only tells you how it's supposed to work. So let me see if we can do that. So the thin explanation goes like this. For illustration, let's assume the P matrix is 3 by 3. So we can assume it looks like P00, P01, P02, P10, P11, P12, and P20, P21, and P22. So that we're assuming that's the general type of probability transition matrix that we have, that it's 3 by 3. Okay, so then do this, change P, P to what I'm calling P tilde. Okay, so what is P tilde? Where P tilde looks like this. It looks like the same first column, the same second column, but for the third column, replace it by ones. Okay. So that's how I'm defining P tilde. Let me see what else I need to tell you. Well, not too much more do I need to tell you. So I'm not even sure. I'm going to put quotes around. I've said thin explanation, and I'm going to put quotes around explanation because, again, I'm just explaining how it's supposed to work, not why. So form the vector U, and the vector U is a column vector that has entries U1, U2, U3. And how do you get a hold of U? So where vector U looks like the following expression. You take the P tilde matrix you subtract off the identity matrix. And then to this matrix that you get, you do two operations. You invert it and you take the transpose. I think I already talked about transpose, and I'm hoping you've already seen what it means to take the inverse of a matrix. So you could show that, well, those operations in two ways. You can say minus t. T means you're going to take the transpose of this matrix, and the minus, well, -1 is up here, essentially. That means you're inverting it. Now, how you do that is sort of up to you. You can take the transpose first and then invert what you get, or you can invert it first and then take the transpose. I don't think the order matters. And that's one of the things I'm not sure about. We'll see. Anyway, you do this, and then there's more. You multiply it by p tilde transpose. These are two different matrices. And this one, you let this work on the vector 0, 0, 1. Okay, I didn't like what I was doing. Let me see what's going to give me that kind of this situation again. Yeah. I'm back, but I don't think you can see it. Okay, I think you're in a place now you can see it again, I hope. And let me see if I can move things along a little bit here. So what did I put in here? I put in the vector 0, 0, 1. Okay, well, that's a complicated expression, to be sure. So let me see if I can explain it in words. The 0, 0, 0 vector is fine. That's just the vector having, well, actually, that's wrong. 0, 0, 1. My bad. That won't get it. Okay. So take the vector 0, 0, 1. Take p tilde transpose times that vector. So you can consider this as a matrix times a vector product, and then also multiply it by this matrix after you do all of this. And when you do that, you're going to get the vector u, which has these components. So I'll just set this whole stuff here equal to u1, u2, u3. Okay. And okay, so after doing that, how do you get what you want? Well, then we say if you take u1 so here's the conclusion. Then you're trying to get pi 0. What are we trying to get here? We're trying to get pi 0, pi 1, pi 2, because we're in the 3 by 3 case. So what I'm saying is that pi 0 will be what you get when you multiply pi 1 by u3 inverted, and pi 1 is what you get when you multiply u2 by u3 inverted. And then in order to finish the deal, pi 0 will be 1 minus these. Not pi 0, pi 3, I guess. Pi 2. Okay, so that's how I think it works, but it's certainly complicated. Let's give it a shot. So what does that mean? Let's test it. We did example 3, so I'm going to need your help a little bit. Either use a calculator or use some computer algebra system like Wolfram or Mathematica or whatever, MATLAB even. And let's see how this would work. So here's how it should work. So let's do a test. And the test is really a test because I haven't had a chance to check it myself. So there's certainly a chance that this won't work. So this is possibly a work in progress. Before I do the test, any questions about what I have here? So I'm telling you a way to come up with pi 0, pi 1, pi 2. That's the objective, no matter what p looks like. So it's a formula, but a complicated one. Okay, so let's do the one in the book and see where it goes. So the one in the book from example 1 that we did the other day, it's on page 49. So there, it's on page 49, as I say, and what was p equal to? So p, so let's suppose that p is 1/3, 1/3, 1/3. 1/4, 1/2, 1/4, and 1/6, 1/3, 1/2. Okay, so that's what p was. And let's figure out what everything is needed for this formula. So we have to first figure out what p tilde is. That's this. Well, p tilde is just like p, except it changes the last row. So p tilde would keep the first row as it is, 1/3, 1/4, 1/6. It would keep the second column, that row, first column as it is, second column as it is, 1/3, 1/2, and 1/3. And then the last column, it would change, according to what I described above, to ones. So it's 1, 1, 1. Okay, so in this case, that's what p tilde would look like. What else do we need? Not much. We know what p tilde looks like. The identity, in case you're not sure, the identity for a 3x3 matrix is just ones down the diagonal and 0 everywhere else. So that's how I looks. So we have what p tilde is. We have what I is. Here's something where I need your help. So what we need to do we need to get a hold of this U1, U2, U3. So this thing says take p tilde, subtract I from it. So let's do that. So if you take p tilde, subtract I, that's really subtracting ones along the diagonal. So this 1/3 becomes 1 minus sorry, 1/3 minus 1, which becomes what, minus 2/3? The first row will be unaffected otherwise. The second row, well, you still have the 1/4 here, that's fine. But then here you subtract 1 from there. So 1/2 minus 1 is -1/2. And the 1 is still there. And what else? The last row is 1/6, 1/3. And then from the 1 here, oh, that shouldn't have been a 1 to begin with. That should have been a 1/2, right? No, that's a 1. I'm sorry. I've got to believe what I'm writing. 1 minus 1 is 0. And in here was -1/2, I believe. So make sure I did that right. It should be the same matrix P tilde that I had, and I just subtract 1s off the diagonal elements. So minus 2/3, -1/2 in the middle, and then 0 there. Okay, so that's that. And here's where I need your help. We need to do 2 things to that matrix. We need to invert it and then do the transpose. And it doesn't matter which one we do first, I don't think. That's something that would be nice to test. So why don't we test that? So let's first find its inverse. Find the inverse of this thing. Well, it'll be a 3x3 matrix. And now we're in a bit of a bind. It's not so easy to do that by hand, nor would I actually want you to. So I would like you to do it some other manner, either with your calculator or some program. And I'll just wait and see what people come up with. So tell me what the inverse of this matrix P minus I is not what we're needing here. Let me see. Yeah, we need to know the inverse and then we'll transpose it later. By the way, how would be a decent way to do it on the calculator? On the calculator, if you have something like a TI 80 something, 89, 83, 84, most of those would apply. You can simply put in this matrix and then just raise it to the -1 power. And what comes out should be the inverse of it. Now, I'm not sure if it's going to come out in decimals or if it's going to come out in fractions. That's a different matter. But I mean, that's one way. That's sort of an easy way to do it if you have your calculator in your hand and you know how to play with matrices on your calculator, enter this matrix and then take the -1 power of it. So that means essentially what I'm suggesting on those calculators is do this and then hit this and to the -1, right? And typically that's what you do. Has anyone done that yet? Maybe more important is anyone in the process of doing it, because we need it to go on. So let me stop sharing for a second and see where you're at. So I will stop sharing. How's it going? Is anyone able to actually invert that 3x3 matrix on their calculator? Or if you prefer to do it online with some software, that's fine too.
I did it online.
Okay.
I can share my screen so we could see it, or
well, how bad does it look before we even? Is it nasty decimals or what does it look like?
they're in fractions, luckily.
They're in fractions. Okay. Well, in that case, let me just hang on. Let me just reshare. Why don't you just tell me the first row? What's the first entry?
All right. Negative 3/4
Minus 3/4. Second,
and 3/4,
okay,
then 15/8,
15/8. Okay, next row.
3/8
Mhm.
minus or negative 3/8.
Okay.
And 33/16.
Okay,
So last it's 3/8 again. And then 5/8 and 9/16.
okay, and this is coming from whom? Who am I talking to?
Isaiah,
Isaiah, thank you. Isaiah, did you do this on your calculator, I assume?
well, there's this website that I use. It's
That's
what's
fine.
yeah, Matrix Rehish, however you pronounce it. Yeah.
Well, okay, here's what I want you to check. Just to make sure this is right and you're doing it right. Can you multiply these two matrices together? Maybe on that same website? You should get the identity if everything is right? Because the matrix times its inverse should get you back to the identity. So if you can do that check for me, then we'll know this is good to go. Or while you're doing that, is there anyone else who got the same answer? No one else. Okay, that's concerning me a little bit because this is an algorithm I want you to be able to use. And now you're making me worried about something else that maybe you don't have a calculator or so what's going on? Are you able? Did you forget your calculator, or do you not know how to do it on your calculator, or where are we? I mean, I don't need everybody to be able to do it right now. I'm happy Isaiah was able to do it, but the whole point of it is for you to use a calculator or some kind of a software. So did anyone else get the same answer?
I don't have a calculator that is that advanced, so,
Yeah, okay, so you don't have something that could invert a matrix or even play with a matrix.
right.
Okay, that might be an issue. Okay, that explains it in Candace's case. What about the rest of you? Teacher, I know, should be able to do this because you've done worse.
I actually just plugged it into my calculator. I got the same thing.
Perfect, Zach. Okay, good. So, all right, now this is a requirement. Let's be optimistic for the moment. Let's assume this is going to work. It's only useful if you can actually do the matrix manipulations. So there's, assuming this algorithm is going to work, even if it doesn't work today, I'm confident I'll be able to make sure it'll be fixable, I'm sure, and be able to work in the future. So let's go forward with this. At least we've got a couple of people, but you do need to be able to do that for, I'm not asking you to do this by hand, because if you had to invert this matrix by hand, that's probably no easier than solving the original equation by hand, or no harder, about the same. Okay, so let's assume this is good. Let's go back to what we need to do next. We need to transpose it, right? So if we transpose this.
Professor,
Yes, please.
I calculated it and it did come out as identity matrix.
Wonderful, wonderful. Thank you very much.
I could show just in case you want to check it out, or
No, I'm happy that you were able to invert it. Figuring out how to invert it I have a feeling that's going to be an individual kind of issue for people. It depends what calculator they have and etc. But I'm going to for now, I'm going to leave that concern in the hands of the students. They have to figure out some way to do this. Okay, so, but I do want to do with the next step. The next step is to take this guy and to transpose it, I suppose. So we've talked about how to do that as well. So today is turning into a bit of a tutorial, how to do something in an algorithmic way. Well, if you transpose it, the main diagonal stays the same. So the -3/4 there is the same. The -3/8 along here is the same, and the 9/16 would stay the same. But these two would switch. So this one would become 3/8 over here, and this one 3/4. And these would switch. So this would be 3/8 up here and 15/8 down here. And the last switch would be these 33/16 would go here and 5/8 over there. And if somebody's got this stuff in front of them, you might want to check what I suggested. Suppose we took the transpose of this first and then inverted it. Would we get the same thing that we just got? I hope so. But if you want to verify that for me, that would be cool. I'm just making sure I get this right. The 3/8 and 3/4 were switched. The 3/8 and the 15/8 were switched. And the 33/16 and the 5/8 were switched. Okay. So where are we on our program? In our little program, we're at this point, we know what this guy is. Now, well, we have a choice. We could figure out what P tilde transpose times this vector is and then multiply it by that. Why don't we do that? So what is P tilde? P tilde is this. And what do we have to do? We have to transpose that guy. So I need to know what P tilde transpose looks like. So P tilde transpose is still a 3/3. And it's this thing. So I'll keep the diagonal the same because that doesn't make change. 1/3, 1/2, and 1. But these get switched. So this one becomes a 1/3. And this one a 4th. And the 1 goes down here. And the 6 goes over here. And the 1 and this becomes 1, and this becomes a 1/3. And I'm just looking to make sure I did it right. So the diagonal doesn't switch. But basically, you get things in the mirror image of the diagonal, they get switched. So the 1/4, 1/3 looks right. 1/6, 1 looks right. And 1/3 without a minus sign. And 1 looks good. Okay. So that's that. And now what do we need to do? We need to go back to the formula. We need to multiply that matrix times 0, 0, 1. Well, that part is something I can do by hand. So if I multiply this by 0, 0, 1, and I'm doing the same thing over here, so I don't know, maybe I should somehow indicate that. So this is really P tilde transpose times the vector 0, 0, 1. And when I multiply this matrix by this, I'm just going to end up with the last row. This times this is just 0 times this, 0 times that, and 1. Oh, no, I'm actually not ending up with the last row. I'm ending up with the last column. So it's a good thing I did it. This times this is a 1/3. And so what is this all equaling? Just 1/6. 1/3. And 1. Okay, so that I don't need any assist on because it's easy to multiply a 3 by 3 by a 3x1 vector. So we got that. And then what's the rest of this program? The rest of the program, go back up here. Now that we've done this much, we've got to multiply this vector that we got here. We got to multiply it by the one that I got with a little help. So that's this one here, right? Okay, so here we go. So we need to complete this deal. We need to take P inverse, subtract off I, take it to the minus T power. And that turned out to be this matrix here, minus 3/4, 3/8, 3/8, 3/4, minus 3/8, 5/8, 15/8, 33/16, I hope, and 9/16. And now we need to multiply that by what this is all. So this is just what? 1/6, 1/3, and what was it, 1? Okay, so because that's what's indicated by the formula up here. We take this matrix, then multiply it by this matrix times this. Well, we already did that product, so that gave us this vector. So we're at this juncture. Okay. And that's good because things are getting a little thick and sort of complicated. So what comes out when you do this product is U1, U2, U3. I could use a little bit of help here. I don't think I want to do the number crunching particularly. So if somebody wants to do this for me and give me the answer, I think it's going to all be everything looks like fractions. So I'm hoping the whole thing here will just be 3 fractions. I'm a little lazy because I'm thinking what? You should be able to do it on your calculator or on some software package. So is there anyone who could do this matrix product this times this?
I think I have the answer, but it's in decimals. That's okay.
It's okay, though. If you could put it in a fraction, that would be great. Or maybe you can recognize it. But I'll take it, worst case, I'll take it in decimals. Anyone have any fractions? I mean, I'm looking at the first product and it looks like maybe I can get it in terms of 24ths. Maybe I'm being too lazy. Let me play with it a little bit. So minus 3/4 times a 6th. And then plus what? 3/8 times a 1/3. And then what? 3/8 times 1. So the first one looks like minus 3/24. This looks like, let's keep it in 24ths maybe. So this is also 3/24, that cancels. So this just turns out to be 3/8.
I have the other entries in fractions now.
Cool. What do you got?
And then it's 5/8. And then 25/16.
25/16. Thank you. And in this case, well, actually, even just doing the first part of the multiplication by hand, it doesn't look too bad, right? It's just a little bit of entering fraction land. So, and did anyone else get the same answer? Who just gave me this? Was this Zach or someone else?
It was Raymond.
Raymond, thank you. Do I have confirmation from someone else? Because it would be cool to be able to know this is right.
I got the same thing.
Perfect. Okay. So this is U1, U2, U3. Okay. U1, U2, U3. And we're almost done with the example. Here's what it says to do. In order to get pi 0, take U1 and multiply it by the reciprocal of U3. So this is the moment of truth. Take U1, multiply it by the reciprocal of this thing, which would be what, 16/25. And that's supposed to be pi 0. U1 is 3/8. So we have 3/8 times 16/25. And it looks like 6/25. And I can't resist. I got to go look and see if that's what's happening in the book. I don't remember. Yes. Back on page 50, when we did this the other day, we got 6/25 for pi 0. So I'm feeling better, but I can't breathe completely because I have to figure out what pi 1 is. Pi 1 was what? It was given up here somewhere. Pi 1 was U2 times U3 inverse. So U2, which is 5/8 times, what times is this again? 16/25. And U2 was 5/8. So this time it's 5/8 times 16/25. And if we do this, it looks like 10/25. And if I check with what we did the other day, 10/25 is what they have in the book. They reduce it to 2/5. Yes, so we're in business. And then how do you get pi 2? Well, I didn't tell you, but you can guess. Pi 2 would just be 1 minus the sum of these two. So it's going to be 10/25 and 6/25. That's 16/25. So I would just do 1 minus 16/25, which is 9/25. And that agrees. Okay, so I'm happy. Why? Because the algorithm works. Okay. I didn't have time to do this check. So I did it in class, which is all fine because this is sort of forcing you into the land of numerical, calculations here. Any questions with how the algorithm works, or hopefully this explains how the algorithm works for the example that we did in class the other day, and we got the same stationary distribution that we got by doing it by hand or following the book steps. Okay. Questions about how the algorithm works? Now, what do you need to know? Well, you need to know the algorithm, okay? The algorithm is this. And by the way, the cool thing about the algorithm, which, since I haven't explained how I got it, you might be wondering, but the cool thing about the algorithm is it works in more general. Otherwise, it would be of limited interest. So suppose that P instead of 3 by 3 was something like 5 by 5. 5 by 5 is going to give you 5 equations and 5 unknowns, linear equations. And, 20 to 30 minutes later, you're either going to arrive at your answer or you're going to be frustrated trying to do it, or you might arrive at an answer and not be sure it's right if you just did it by hand. But what I'm suggesting is do the same algorithm. So if this thing were 5 by 5, I would still form P tilde the same way. I would keep the first 2 columns of P the same and replace the third column by all ones. I would form a vector, but this time it would have 5 components instead of 3. But it looks pretty much like this. This part looks the same. This part looks the same. This part will look like 0, 0, 0, 0, 1. So it'll be a vector that's 4 zeros and then a 1. So other than that, you know, the algorithm is the same. And what would come out if you did it for the 5 by 5 case would be U1, U2, U3, U4, U5. And then how do you get the pi's? Well, you do what you did here. So this part of the formula is exactly the same, well, except you don't divide by, it's not U3 inverse, it's U5 inverse. And then this one would be U5 inverse for this, and then there'd be 2 more. So it would be pi 2 would be U3 times U5 inverse, and then pi, let me see if I'm doing this right. Yeah, so the other ones are pi 2 would be U3 times U5 inverse. Pi 3 would be U4 times U5 inverse. And then the last one would just be 1 minus the previous 4. Okay, so do you have a feel for how this would work? Okay, so now we have 2 things to consider. And not much time to consider it, but a little bit of time. Should we do one that's worse, just to make sure we have the computative skills? Or should I actually do the explanation of where the algorithm comes from? And I think I'm going to answer my own question. Why don't we try a 5 by 5? Because I'd really like you, the real takeaway I want you to have is the computational way to do this. I pretty much doubt that the proof of it will be something that I'll require you. I mean, I'm going to probably give it in class, so I don't want you to just look at it as a magic formula that came out of the air. But for this moment, probably using it would be more the idea. So let's create an example. Should we press our luck and stay with the same page? Sure, for now. So, okay. So let's create an example and let's try 5 by 5, because 5 by 5 is big enough to be something you don't want to do by hand yourself. And yet you might want to find the stationary distribution. So let's create some states. How about 0, 1, 2, 3, and 4. Now, what's the main requirement for this algorithm? You have to have an irreducible Markov chain. So every state has to communicate with each other. Other than that, I don't think there's much here to worry about. So let's put in some arrows and we'll put some numbers in soon. So suppose you're going from here to here to here. And maybe to here. And to here. So far you can get many places, but you can't necessarily get back. So let me put in maybe an arrow here. An arrow here. And is that enough? No, I don't think so. Once I leave 2, I can never get back to it, right? So I need a way to get back to 2. Yeah, because I'm looking at 4. Well, no, 4 can get to 2. Do I need more arrows for this to be irreducible? If I'm at 2, I can get to 3 and 4 and 1 and 0 and 2. Yeah, so I can get anywhere from 2. If I'm at 1, can I get everywhere? Yeah, I guess so. Is that right? All right, so maybe instead of creating a horrible monster, is this bad enough? And what does bad enough mean? Does everything, is this irreducible? Do all states communicate with each other? So if you're at 0, can you get everywhere? I certainly can get to these 2. I can get to 3 and therefore 4. So from 0, I can get everywhere. From 1, can I get everywhere? I can get to 0. I can get to 1 eventually, it won't be in one step, but who cares? I can get to 2, I can get to 3, I can get to 4, back to 1. I think I can get everywhere. From 2, can you get everywhere? Yes. From 3, I believe so. And from 4, yeah. So I think this is an irreducible chain. Okay, so what does P look like? From, oh, I need numbers. Okay, so since there's no other arrow here, I guess this could just be 1. I'm trying to keep it rather simple. Why don't we make these a half? From 2, it looks like you got to go here, so that's a 1. From here, it looks like you got to go there, so that's a 1, and this is a 1 back. Okay, so this isn't bad at all. So what does P look like? Where can you go from 0? You can go back, you can't go back, but you can go to 1. In one step, you can't get to 2, nor 3, nor 4. So that's the first row. From 1, where can you go? You can go down to half, or you can go up to 2, and that already adds up to 1, so that's it for that. From 2, where can you go? Only one place, to 3. So can't go to 0 or 1. Or 2, but you can go to 3. From 3, where can you go? In one step, you can't get to here, here, here. You could only go to 4. So 3 to 0, 0, 3 to 1, 0, 3 to 2, 0, 3 to 3, 0, and 3 to 4 is 1. And finally, 4, where can you go? Only one place, right? 1. Okay. Let me make sure. The rows should add up to 1. They're all probabilities. That's it. Hopefully it's irreducible. What do we want? We want oh, the theorem says if you have an irreducible Markov chain, then there's a unique stationary distribution, and we want to find it. So we want to find pi such that what? Pi is equal to pi p. Okay. So we already have what p is. Let's start doing this problem as we did before. What was the first step? The first step was to replace p by p tilde. So p tilde is what? Still going to be 5 by 5. First column doesn't change. 0, a half, and 3 zeros. Second column doesn't change. 1, 3 zeros, and a 1. Third column doesn't change. 0, a half, 3 zeros. Fourth column doesn't change. 0, 0, 1, 0, 0. The last column becomes all 1s. Okay, so that's what p tilde is. Next stop. Next stop, the algorithm up there, wherever there it is. So how would this look? Let me see if I've got it written here anyway, so I don't have to scroll up and down. So let me just go down right next to the example that we're doing. And we need the u vector, which this time has a u1, a u2, a u3, a u4, and a U4. And the U5. And what is it equal to? It's equal to find P tilde minus the inverse. Inverse is 5 by 5 inverse. Take the inverse minus transpose of this, multiply it by P tilde transpose, and multiply it by 0.00001. Okay. Yeah, I've got my usual Friday noise outside, so let me see if I can wait a second while this guy passes me, maybe. Okay, once we get a hold of the U's, what do? Then I0 will be U1 times, what is it, U5 reciprocal? I believe that's what I had before. Let me see. Yeah. And pi1 will be U2 times U5 reciprocal of that. I0 will be U3 times the reciprocal of this. That's 3. Try 2. Okay. I3 will be U4 times U5 reciprocal. And then pi4, the last one, will just be 1 minus all the others. Okay. So this is actually turning out to be pretty much on cue. Our class time is up, but we have all the pieces we need to put into the algorithm because we have what P tilde is. We can subtract the 5 by 5 identity matrix. This is the hardest part. We need to take the inverse of this matrix and the transpose as well, but the transpose is not hard. But finding the inverse of a 5 by 5 is not something I would want to do by hand in general. So that's what we need to do. We can form this difference. We need to take its inverse and transpose it. And then this guy we have, and we could easily just transpose this ourselves. So we could even do the multiplication here. So the objective next is to find the U's, U1 through U5. And the snag or the hard part is finding the negative transpose of this thing. Once you have that, then you're just multiplying that matrix times whatever that's over here. And, you know, with this kind of setup, I'm thinking the U's are going to be pretty nice. Let me just ask, has anyone already done this as I've been talking? Does anyone already have the U's? No. Okay. So I think this will become homework. Okay. Homework, complete this problem. And please, I'm not asking you to do it by hand, so please don't do it by hand. First of all, that's not the point. The algorithm is that this is to force you to do some horrible calculation by hand. The point of the algorithm is to use either your calculator or some package, preferably your calculator, if you have a scientific calculator which allows matrices. All you need is a calculator that allows matrices and allows you to take the inverse. Okay, so I will leave this as a homework problem. Be careful. Oh, well, 2 points. How do you know you got the right answer? Well, you're going to get, if you're all done here, you're going to get pi 0, pi 1, pi 2, pi 3, pi 4. And it should be easy enough to go back and check whether this is true. Because once you have your hands on the pi, it's a simple matrix multiplication of multiplying this matrix by this to see if you got that. If you got that, then you've got it. And the theorem tells us there's a unique solution to that, so you're able to find it. So it's easy enough to check whether it's right or wrong. That you could actually do by hand if you wanted to, but certainly you can do it on the calculator as well. So that's a good point, is that it's easy enough to check this thing.
Professor, I have a question.
Here,
What if our matrix is an invertible?
if the matrix is not invertible, then, and that's actually the next thing I was going to say, then one of two possibilities. Since I made this up on the fly, you saw me make it up. It's possible that this is not irreducible, perhaps, but I think it is. So if yeah, you're asking me, what if you can't do the algorithm? What if it's not invertible? I'm thinking that as long as the Markov chain is irreducible, then it should be invertible. So if you get to this point and it's not invertible, then either I gave you a bad problem from the beginning and it's not irreducible, which I could double check, I think it was, or you made a little error along the way, just put in the wrong entry someplace. And that, that's easy to do too. Okay. So the answer is theoretically, if it's irreducible on the whole state space, there's only one state, there's only one equivalence class, this should work. Because,
Okay.
And if not, either I gave you a bad problem from the beginning, or you just sort of dropped the ball along the way. Did you get that in this case? Did it turn out not to be invertible, or you're just asking?
I was just wondering for future like cases.
Yeah, okay. Yeah, no, this should work. That's the nice thing. And if I had to give a quick idea of what's going on, here's the quick idea of what's going on. I've already told you that this equation is not easy to solve because P doesn't have full rank. That means if you write out the linear equations here, they're not all distinct. At least two of them are the same. Usually, in fact, so what we did is replace P by P tilde, and this thing has full rank. And that's the main idea of what I did to get this algorithm. And I think it follows what I've even been telling you all along. You got to use that last equation that all the probabilities add up to 1. So I incorporated that equation into P tilde, which is sort of a modified version of P. So I took out one of the equations and put in that equation. By the way, I don't think it matters where you put it. You could take out any of the equations and just put a column of 1s. Anyway, once you do that, then you're solving this system of equations, and it should be invertible. And the easiest, now in general it won't be. If somebody just throws you a P matrix and asks you to find the stationary distribution, if you try to use this algorithm without checking, you may end up finding it's not invertible. And what does that mean? That means the system is not irreducible. All right, so let me just ask, did anyone find an answer to this yet? Some people are better with this stuff than others. This is, I suppose, some use of technology, right? I'm curious what the answer is. I don't know because I just made it up. Well, okay. So one could ask, so if I want to go skate on thin ice, which is an expression for take a dangerous trip, I could go back to the matrices in chapter 1. So yeah, let me just offer this as something. Look at the matrices. So here's an afterthought. Consider or reconsider problems 19 and 20 on page 44. Now, I think we already did it. 19, I remember, was not irreducible. So that means it will not necessarily, it will not have a unique stationary. But I don't remember what the 20 is. So the question is there a stationary distribution? So let's say, is there a unique stationary distribution for these two problems? I think the answer to 19 is no, because I remember it's sort of, the equivalence classes were not, there wasn't just one equivalence class. I think there was 2 or 3. So if there's 2 or 3 equivalence classes, then there will not be a unique stationary distribution. So I think the answer to my question on 19 is no. But I don't remember the answer to my question on 20. And the reason this comes to mind is the matrices are already given there. So it might be fun to think about it. Okay. I'm done with today's lesson. I'm going to take a little water break and come back and do the office hour. And I'm fine helping you do some of the technology, and if people are trying to learn how to use their calculator or how to do this kind of problem. I'm happy to talk about that during the office hour, or of course other things too. So I'll see you in about half a minute here. I'm just going to sip some water. By the way, if you were a Dodger fan, you were happy with yesterday's results. Okay, I'm back. Request. So what do you want me to look at? I mean, the obvious answer is this problem right here.
Hey, Professor,
Yeah,
I actually had, I know we kind of covered this a little, like maybe a week ago, but I had a question about the proof of equation 68 from the book.
sure. Pardon me, let me write down. Proof of 68 from the book. Okay, so yeah, I'm happy to talk about that. I think anything we've done in the past is certainly fair game. But let me see if anyone else has anything else. So this is a good time to make a short list of things. So I'm throwing the homework in on the list just in case no one asks anything else. And when I say homework, I'm thinking of this particular problem. Or is it this problem here, finding the stationary? But yeah, I'm happy to go back and look at 68. Anyone else have any other requests? Okay. Well, why don't I take the request from you guys first? I'll take the request for 68. Let me see if I can get to that material easily. I think it's. Okay, it's on page 33. So sure, what's your question?
So on page 32, after equation, the paragraph after equation 63, there's a sentence that says, hence the event t sub 0 is less than t sub n for some n greater than 1 occurs if and only if the event t of 0 is less than infinity. And I guess I was just confused with that statement. Like, is that saying that those sets are the same?
Yeah, let me see. So you're talking about the sentence right under 63, right?
Yeah.
All right, so let me read it again. Equation 62 implies that Tn is greater than or equal to n, and thus Tn goes to infinity as n goes to infinity. Okay. Hence, the event occurs if and only if this. Therefore, we can rewrite it this way. Okay, so yeah, I understand what they're saying. Give me a second just to look at what preceded this. Yeah, so here's my takeaway of what's going on here. Okay, give me one more minute to reread this. Yeah, so they're basically coming from 61. So from 61, if you're okay with that point, let me just start there. So 61 says the following. That if you start at state 1, the time it takes to hit 0 for the first time is less than the time it takes to hit n for the first time. And 61 says that this expression is equal to this. Summation over y. That's a y, sorry. Or is it a gamma? I can't even say. I think it's,
I think the index is supposed to be y.
yeah, I think it's y. So with y going from 0 to n minus 1 of gamma y. And then off to the side somewhere n is bigger than 1. Okay. So you're okay with this equation, I assume. It came earlier.
Yeah.
Okay, what they want to do, they want to take the limit of both sides as n gets large. Now, the easy one to see what's going on as n gets large, this infinite sum will be going from y equals 0 to infinity. So if you just did it, if you just assume that this expression holds, and you want to therefore say, if I take the limit of this side, it's equal to the limit of that side, following the, the old idea that whatever you do to the equation, as long as you do it to both sides, you get a new equation. Okay, so if you're allowed to do that, then the limit as n gets large, this one becomes 1 minus 1 over the sum of y going from 0 to infinity now. Gamma y. And now you're left to worry about what's the limit as n gets large of this stuff. And what they want to say, they want to say that the limit of this is what happens if you just let the limit, if you like take the limit through the P1 parentheses and put it inside. Well, if you did that, let me just do it and then we'll talk about why it's legal or not. But they're really putting the limit through the probability. So when you do that, if you bring the limit into the parentheses here, the t to 0 doesn't change because there's no n. And the inequality looks the same, but you're taking the limit of this side of the inequality as n gets large. So intuitively, what they want to do is take the limit of this quantity by bringing the limit inside. Stick with that idea for the moment. If you know as n gets large, the time starting at 1 to hit n will also get large because things are going up one step at a time. It's a birth-death chain. So if you just put the limit inside, and you think of as n gets large, this thing gets large, then this would turn into what? P1, T0 less than infinity. Because the time it takes to first hit n, starting at 1, as n gets large, is becoming bigger and bigger. Because you can picture n is just receding to the right. That's what they want. So they want to take the limit of both sides of this. And in this case, it's easy. You just let this go to infinity. In this case, they want to argue that you can take the limit inside and that this then becomes infinity. And then this becomes something they know, namely what? Rho of 1, 0, I think.
Yeah.
So for them, what they're worried about is the justification of going from here to here. Why can you take the limit inside? And I think I talked about that a little bit briefly as we did it, but it's not rigorous. First of all, what they say is you can do that by a theorem in the earlier volume of their work. So that's what they're saying. They do give a little bit of an idea of what's going on. The things inside here, if you think of this as a set that depends on n, you're finding the probability of some event that depends on n. They're saying that as n gets larger, what did they say? That this thing inside actually forms a non-decreasing sequence. So they're saying that these things are getting bigger. And it turns out that there's this result that if you take the limit of a probability of a sequence of sets that's getting larger, then you can just take the limit inside and whatever these sets converge to, which happens to be this situation, is legal. But we certainly haven't done it in this class. There's a small irony for those few folks who are in both my classes. This kind of manipulation where you're taking the limit of an increasing sequence of sets is something that I've done in my graduate Rio analysis class. So there's maybe two or three people who are in both my classes would actually know the reason why that holds. But for everyone else in this class, there's absolutely no reason you would know it. And the authors know it as well, so they actually refer it to their book. So, but yeah, so what's going on from here to here? They are saying that they can take the limit inside and get this, and therefore the rest follows. And they're saying that's true because what's inside describes a sequence of events that are non-decreasing or increasing. But even though they explain it, it's not obvious that that would be true. So I don't know if I've given you enough, or did I cover somewhere in that explanation what you were looking for?
Yeah, it definitely does help.
Okay.
I guess I was reading into that paragraph a little bit too much. I guess I was just trying to understand on an intuitive level why the event where the time it takes to hit 0, or you hit 0 before you hit n, occurs if you reach the time it takes to hit 0 is less than infinity. But I guess that
Well, yeah, the infinity is coming about by taking the limit inside. And then you've got this picture to deal with. You've got the birth death chain. And in this case, you're starting at 1. So you're starting here. And where you want to end up, well, from 61, wherever that is, that's up here. So then you're looking at the time it takes to first hit n. N is pictured as being way down here somewhere. You know, there's the usual birth, death, up and down business.
Yeah.
With maybe some loops, but whatever. So you're starting here, and they're trying to say, what if you start there, the time, what this says, the time it takes to first hit n will be larger than the time it takes to first hit 0. So that, and that would actually make sense if this is far, if n is far away, because there's a better chance you'll hit this first than you hit this.
right.
So that condition makes some sense. And then they're saying what happens to this picture as n gets large. So as n gets large, then the time it takes to first hit n gets bigger and bigger. And that means the chance of hitting 0 first is going to be bigger than, is getting better than it was before,
Right.
because your goal on the right side is getting more distant. Maybe that helps a little bit.
No, it does. It does.
Okay. Any other questions before I go back to the homework here? So let me go back to the homework. I'm glad you were interested in that question though, because that's one of the more subtle points and it's not fully explained there in the book. Okay, so back to the homework. Did anyone get an answer? Did anyone get, you know, I've explained already the algorithm and what to do here. Did anyone actually work it out and get pi 0, pi 1, pi 2, pi 3, pi 4?
Yes, I did the problem.
Oh, fantastic. Okay. Can you tell me what you got? So,
I got pi 0 equals 1/6, pi 1 equals 2/6, pi 2 equals 1/6, pi 3 equals 1/6, and pi 4 equals 1/6.
so everything was 1/6 except for pi 1, is that right?
Yes, pi 1 was 2/6.
Got it. So the answer is nice. Yeah, if your answer is right, and I hope it is, right? Well, we can check that, right? So let's see, pi 3 was 1/6. Pi 4 was 1/6. And pi 5, I think you told me was also 1/6. Is there 5 or was 4 at the end of the one? It's
That's only 4.
only 4, so that's it. That's it. Okay. So let me just make sure that at least the obvious thing, does everything add up to 1? And it does. Okay, so at least it's a distribution. And let's actually just, without doing it myself, but we can easily check whether pi is equal to pi p, right? That would be the easy check. Why don't we do that? So where's p? P is up here. So, okay, I have to, let me write it this way. So is it true that 1/6, 2/6, 1/6, 1/6, and 1/6 is the same as what you would get if you take this vector, 2/6, 1/6, 1/6, 1/6, and multiply it by p. And the problem is I don't have p memorized, but it's up here someplace. It's, yeah, so this one is 0, 1, 0, 0, 0. And the other next one is this 1/2, 0, 0, I believe. Okay, that's the first 2 rows of p. And the next 2 rows would be just 1 either in the second to last or the last position. Okay. Was it second to the last for this one? I forgot already. One of them has a 1 here. It's either a 1 here and here, or the reverse. Let me go back and see what I need. It's the what I have. 3 zeros, a 1 and a 0, 4 zeros and a 1. Okay, that's cool. And then the last one was what? The 1 in the second position. So it's simply this 0, 1, 0, 0, 0. And now it's just a simple matter of checking that everything works. So if I multiply this vector times the first, where's my cursor? Oh, I see. If I multiply this by this, I'm just going to get 2/6 times 1/2. And so that's going to give me 1/6. So this one works. And if I multiply this row by the second column, I'm going to get this times this is a 6th, and then I'm going to, all of these are going to be zeros, and then this times this is a 6, so that's going to give me the 2/6. So far things look good. And then multiplying this by the third column, there's only a 1/2 here, so I just have to see where a 1/2 times this, and that gets me a 6, so that's correct. And then if I multiply this row vector by the fourth column, I'm just going to, everything's 0 except for this, so I'll just get the 6th. And then finally, the last one, multiply this row vector by the last column, that's also a 6. So I've just verified your answer, it's good. And so good. So this has a nice answer in terms of an answer. There's after a long period of, well, okay, we got to be careful. This is the stationary. But if the stationary distribution is the same as the steady state, and frequently it is, this would say after a long period of time, there's twice the probability of being at 1 as there is anywhere else. Let's just see if that makes some sense in terms of the picture. Yeah, because everything sort of runs through 1. But anyway, I'm happy with your answer. How did you get it? And yeah, how actually did you get your answer?
I just used the, I guess, the algorithm and plugged it into the calculator. I don't.
Okay, well, that's what I'm asking. You used your calculator.
I used a website, but yeah, I used an online calculator.
Okay, so I'm sorry, what kind of calculator?
It was on Symbolab.
Okay, that doesn't mean anything to me, so. Okay, but you were able to get it to work on your calculator. Okay, I'm happy. You're an existence proof. You've just shown that someone could do what I was trying to teach you on your calculator. So thank you. Is there anyone else who tried to do it on their calculator?
I did it and I got the same answer.
Fantastic. Okay, why am I asking this stuff? I want this to be a test problem on their next midterm. You're allowed to use the calculator, right? So that's where I'm, and by the way, I can't give you this problem without the calculator, because then you'll spend a half hour trying to find the inverse or something, and probably not get it right if you're like me. So what I'm trying to get is that people, this is a good test problem right here. How long did it take you to do it on your calculators?
Not too long.
Wow, that's rather vague.
Yeah, I don't, I would say like maybe like 6 minutes.
Okay, that's good. If it's 10 minutes or less, that's the kind of problem I want. Okay, I don't want it to be tough. I'm 15, I can live with. Okay, so be warned. We want you all to have an ability to answer this kind of problem, the one we just did. I guess I should scroll up instead of, yeah, this one right here, by calculator. And I'm hoping it should take you more than 10 or 15 minutes. I've got a couple people who did it, so that's encouraging. For those who haven't done it, if you're stuck or need a little help, maybe I can help you, or maybe some of these other students can help you as well. So please speak up. Like where you got stuck. Okay. Did either of the two who did this get a chance to look at problem 20 in the previous chapter? Is that irreducible?
No, not yet, sorry.
No, it's fine. I'm just running with you guys because you know how to do the calculator. So, this is not easy to teach in this sense that, well, in order to get you all up to speed to do this problem, there's multiple calculators out there. You need to have one that can deal with matrices. So I already talked, I think there was one person at least who has a calculator but doesn't have one that deals with matrices. Who was that? Refresh my memory.
That would be me.
Okay, that's Candace.
Yes.
Okay. Do you have any access to a calculator that has matrices or?
Not an actual calculator, probably software.
Yeah, but then I get into the problem for the exam. So,
Right.
so you got no TI-80s in your household somewhere.
No, I think the one I did until my son went away to college.
And he took this calculator with him, right?
He did.
Well, that's what you would hope. Okay, I think it would be worse if he left it at home, then you'd know it wouldn't be being used. At least there's a chance he's using it. So that's good. This is,
I'll see what I can find.
yeah, this is the unfortunate thing with virtual learning. If I were at school, I have some extra calculators somewhere in my office, which I would not even know where at this point, that I could simply lend you, okay? And maybe I can still do that through connecting someone at school, if you're willing to go to campus someday and pick it up. So, and is there anyone else beside Candace who would also be interested in me providing you a calculator that would lend itself to this kind of problem? I've done that before, where because I have some TI-89s. That's been they've been around for a long time already, but they do this kind of matrix. I mean, the main thing we need is the ability to invert a matrix. That's what the algorithm calls for. That's the time-saving aspect of the calculator. So Candace, you work it on your side and I'll work it on my side, okay?
Okay, I'll let you know on Monday.
Yeah, if you have a family member or extended family member or friends who have a calculator that you can borrow for a short time, or I don't know, for some time, whatever, and then it's a matter of learning how to. I think learning how to use it wouldn't be that hard. Even if they don't have the manual, you simply can go online and most calculators explain how to do the matrix operations. So, okay. Let's see, let me know. And if you don't have any luck, then I may be able to provide you something. Anyone else
Okay.
in that condition? I shouldn't call it a condition. I don't know what to call it. Anyone else who needs a calculator? Okay, I don't have anything more to do. I mean, there's the explanation of why this algorithm works. I could, but to be honest, I'm just pleased that it works because That's also an interesting point. I've done this before when I've taught the class. It's not from the book. And I haven't seen it in other books. So the explanation of it is to my mind is not bad. But when I actually saw what the formula looked like, I was a little worried that maybe it was wrong or I remembered it right, and I'm glad it works out. So I do want to go through the explanation of why it works. Just so, I mean, the point is that it gives us the ability to calculate things we weren't able to do easily before. But I also would like to explain what's going on here a little better. If there's, okay, so I'll leave it to you. If anyone wants to see the explanation now, I could do that, particularly since I don't have any other problems to address. On the other hand, if you're ready just to move along and then wait for next time, I will do it in class next time. So it's up to you.
I have a quick question as well.
Sure, go for it.
Are we gonna have another midterm and then the final?
Yep.
Do you have an idea of when the second midterm will be?
Yeah, I have an idea, but not enough to tell you or firm it up. Okay.
Okay.
Yeah, but not too far. What week are we in? Are we in 9 or something?
I think we're week 9.
Yeah. So we're in week 9. What I told you before is roughly every 5 or 6 weeks. So 11 might sound like a rough answer.
And then, do you have any plans to get the research group to meet this weekend, or is it not looking?
No, it's not looking good. I'm frustrated. I have people interested in the research group. I'm interested in the research group, but I'm swamped with other things that are just keeping me from doing that. I'm hoping to get, and that's the same problem with the exams, to be honest. Okay, there's just still too much on my plate right now to do the research group. I'm hoping for a little relief next week, but next week's looks pretty bad as well. So I'm sorry. I haven't. This is unusual. I've gone like most of the semester without really meeting very much at all. So I'll let you know when I see some time. Okay.
Okay. It's no problem, Professor.
Yeah. No. It's not through lack of interest, and it's not through lack of anything. You know, I want to do it, but I'm pressed on the time aspect.
Well,
Okay,
sounds good. Thank you, Professor.
you're very welcome. Thanks for asking. I appreciate the interest. Okay, I'm hearing no other requests, so I'm thinking of just signing it off. Play with this algorithm, see if you can get it to work on your calculator. At least it's working. All right, so take care.